All right, with this video, I'm going to do kind of the same thing I did in the previous video where we're going to explore inverse functions. What's going to be different between this video and the last one is I'm going to start out with a more challenging function, and I am going to go a little bit quicker because we won't just be learning this stuff for the first time. So I'm going to do three things. I'm first going to figure out the inverse of this function, then I'm going to compose together a function and its inverse. It's kind of a check, and then I'm going to look at the graphs of the function and the inverse and kind of see the symmetry that we talked about in the last video. So first, let's find the inverse of this function. The first in the four-step process that I taught you in the previous video is pretty simple, so simple that you might not even think it's necessary. All I'm going to do is change the f of x into a y. That's it. I'm literally going to copy exactly what I see here, except instead of an f of x, there's going to be a y. The next step isn't a whole lot more complicated than the first step. All I'm doing here is I'm switching my x's and my y's. So instead of y equals 2x plus 1 over 3x minus 5, I'm going to have x equals 2y plus 1 over 3y minus 5. I have two x's over here, so I got two y's here. This y changes into this x. Now I'm done with step 2. You might be wondering, is it really necessary to have step 1 and step 2? Couldn't I go straight from this line down to this line, change my f of x into an x, and change all these x's into y's? Absolutely you can. I go through this series of steps because I think it has a little bit more intuition behind it. I have something written in functional notation, so first I change it into an equation, but this equation represents the function. What I want is an equation that represents the inverse function. Inverse function, that's just where you switch the inputs and the outputs of the function, so it makes sense to switch the x's and the y's. And now I have an equation that represents the inverse function. So what I'm saying is, yeah, go straight from here to here if you want, but at your own peril, it might be worth the 10 seconds it takes you to write this as an intermediate step. My third step, which is really 90% of the work in these, is solve this equation that I have here for y. And if it helps me anyways, to think about why you're doing what you're doing. The reason I want to solve this for y is because it's an equation right now that represents the inverse function, but I need to know what the inverse function itself is. And to figure out the inverse function, I need to write it in functional notation. And to have something written in functional notation means to express the output of the function in terms of the inputs. So the output is the letter y. I need to get that all by itself and have it written in terms of x or x's so that I can write it in functional notation. The problem with inverse functions is solving this equation for y is different. It's going to be different in every problem you do depending on what the original function was. In the previous video, we saw how to do it if we have a linear function, but here we don't have a linear function. We have what's called a rational function. And I wish I could just tell you how to always solve these for any problem, but really I can't. What you have to do is kind of think about, okay, what kind of function do I have and how do I solve that specific equation? In the case where you have a rational function, or more specifically when you have your variable in the denominator, often it helps to get the variable out of the denominator. I wish this y wasn't down on the bottom here. Well, I can get it up to the top if I multiplied both sides of the equation by 3y minus 5. If I multiply the right side of the equation by 3y minus 5, it cancels with this. If I multiply the left side of the equation by 3y minus 5, well, then I have x times 3y minus 5. It's worth pointing out that no, you cannot cancel out these two y's right here. The reason why is you can't cancel over addition and subtraction. Because you have this plus here and or this minus here, it prevents you from being able to cancel those out. That gets me this far. Common mistake is, oh, now it's super easy. Subtract 1 and divide by 2 and I'll have this y all by itself. That's true, you would have this y all by itself, but you can't solve for y in terms of y. Because there's two y's floating around, you have to get all of the terms that have y's in them on the same side of the equation so that you can turn them into just a single y. What I'm saying is at this point, I want to get rid of the parentheses so that I can collect my terms that have y's in them. To get rid of the parentheses, I'm going to distribute these x through and get 3xy minus 5x is equal to 2y plus 1. The way to view this is as four terms. The first term is 3xy, the next term is 5x, the third one is 2y, and the fourth one is 1. And if you view this as four separate terms, you might recognize that two of those terms, namely this first one and this third one, have the letter y in them. And since my goal is to solve for y, I want to get all the terms with y's in them together on one side of the equation and all the terms without a y in them on the other side of the equation. So one way I could do that is subtract 2y from both sides and add 5x to both sides, and that would give me 3xy minus 2y equals 1 plus 5x. I keep saying that our goal is to get all the terms with y's together on one side of the equation, but I haven't told you why you want to do that. The reason you want to do that is now we can factor. We have the letter y written twice here, which is not ideal. What we want is the letter y written just a single time so that we can solve for the letter y. Remember, that's my goal here, is to solve for y. Well, the way I can change two y's into one y is by factoring. I could pull a y out from both of these terms, and what I'd have left is 3x minus 2 on the left-hand side. A lot of students have a hard time going from this line down to this line, but again, I would make the argument that, well, if you started with this line, would you be able to get up to this line? Like take this y and distribute it through the parentheses? Most students say, yeah, sure, no problem. Well, if this line is the same as this line, then this line must be the same as this line. The advantage with this line is, again, the letter y is only written a single time, so it's pretty easy to solve for it. Just get rid of the rest of this stuff. How do you get rid of stuff? Well, it's divide by 3x minus 2 because the 3x minus 2 is being multiplied by this y. If I divide both sides of the equation by 3x minus 2, I'll get 1 plus 5x divided by 3x minus 2 is equal to y. At this point, all the heavy lifting is done. However, I guess we should do the fourth and final step where we change the y into f inverse of x just to write this in functional notation. I got f inverse of x is 1 plus 5x divided by 3x minus 2. I don't think it's at all obvious how you would get from here to here. I mean, you kind of see 1s and 2s and 3s and 5s floating around in both the equations, but I don't think it's easy to get straight from here to here, especially if I kind of change the numbers that you saw. You don't need to worry about any of that. If you're given a function, here's how you can find the inverse of that function. And if that function is a rational function like it is here, these tricks that I'm showing you, where you kind of get the variable out of the denominator and then get rid of parentheses, and then often there's a factoring step at the end, will allow you to solve for y. At this point, you could check your answer by composing the two functions together, and I'm going to do that. I'm just going to do it once. I mean, you could check f of f inverse of x and then f inverse of f of x and make sure that both of them are equal to x, and that would make you feel really good about this function being the inverse of this function. But really, you don't need to check your work all the time in this class. I'm going to do it one more time just to teach you some algebraic skills and kind of remind you a little bit about function composition. The way you figure f of f inverse of x is work from the inside out. So let's replace f inverse of x with what we just said f inverse of x was equal to, 1 plus 5x divided by 3x minus 2. So what I now have is f of 1 plus 5x divided by 3x minus 2. And since I know what f of x is, namely this thing over here, I can take this expression and put it into f of x by copying what I see here, except replacing all of the x's with what's inside these parentheses. So I'll get 2 times something plus 1 for this 2x plus 1 divided by 3 times something minus 5. And those somethings, instead of being the letter x, will be 1 plus 5x over 3x minus 2. And now this is a huge mess, and you're like, I'm never going to be able to simplify this. But the steps that we do to simplify this will end up being fairly important. So I want to demonstrate them here, even if it's not really necessary to be able to do it at this point in the class. The first thing I want to do is kind of get rid of parentheses. Generally speaking, when you're trying to simplify things, often it helps to get rid of the parentheses. So I'm going to take this 2, and I'm going to multiply it to get rid of these parentheses here. It's tempting to take this 2 and hit all the terms on the top and on the bottom, but you don't want to. You want to view this 2 like it's 2 over 1. And 2 over 1 times these parentheses would give me 2 plus 10x divided by 3x minus 2. And then I'd still have this plus 1. Similarly, if I think of this 3 as 3 over 1 and distribute it into these parentheses, I would get 3 plus 15x, hitting both of the terms in the numerator, divided by 3x minus 2. Again, note I'm not touching the denominator, minus 5. There's lots of ways to simplify this thing, but I think the method that will be the most useful to you is think about you don't know how to divide this huge mess by this huge mess, but if it were just a fraction divided by a fraction, maybe you would know what to do. And if you don't know what to do, don't worry, I'm going to show you in just a minute, but think in your head, fractions divided by fractions are good, but this big mess, this sum of a fraction and a whole number divided by this big mess, the difference of a fraction and a whole number, that's not good. So I want to rewrite this so it's one fraction divided by one fraction. How can I do that? Well, I need to get a common denominator up here in the numerator. So just looking at the 2 plus 10x divided by 3x minus 2, if I think about this 1 as 1 divided by 1 to make it a fraction, I could make these two fractions have the same denominator if I multiplied the top and the bottom over here by 3x minus 2. It's really important that I multiply the top and the bottom by 3x minus 2 because otherwise I'm going to change the value of this thing. My goal is to simplify but not ever change the value. So as long as I do the top and the bottom here, I'm really just multiplying by 1. This is just a strange looking form of the number 1. And as long as I'm just multiplying by 1, I'm not changing anything. Similarly, down here in the bottom, I would leave the 3 plus 15x completely alone. That's going to be divided by 3x minus 2. And then I would say, well, I want to think about this 5 as 5 divided by 1, but I can't subtract these two fractions because they don't have the same denominator. So to get them to both have the same denominator, I would multiply the top and the bottom over here by 3x minus 2 over 3x minus 2. In this case, the denominator here was the same as the denominator here, so there's shortcuts that we could have done to cancel some stuff out, but I don't think it's beneficial to do that because I want to show you a method that works even if this 3x is 3x minus 2 and this is, I don't know, 4x minus 7 or something. It looks like it's getting worse. This looks way worse than it was originally, but it's actually not that bad. Because I have a common denominator here, if I could just get rid of the parentheses, I'd be able to make this a fraction divided by a fraction, at which point I'm in really good shape and I'll be able to finish the problem up. The way I get rid of the parentheses, well, up in the numerator, there's not much to do because 1 times anything is just anything. So I got 3x minus 2 over 3x minus 2. Down here in the denominator, there's a little bit more work. First off, I want to get rid of these parentheses. So you might think multiply the 5 through, and you can do that, but if you just multiply the 5 through, you have to remember that you're subtracting the entire thing. So it might help to, instead thinking about it as multiplying a 5 through, think about you're multiplying negative 5 through. So I get negative 15x, and then negative 5 times negative 2 gives me positive 10, and that's over 3x minus 2. And because I took the negative 5 and distributed through, I'm not subtracting anymore. This becomes a positive. If I stare up at the numerator here, I have the same denominator, 3x minus 2, so I can just add up the numerators. The 2 and the negative 2 will cancel each other out, and the 10x and the 3x will leave me with 13x. So I have 13x over 3x minus 2, which was my common denominator. Down in the denominator here, I got 3 plus 15x plus negative 15x plus 10. Let's see, the positive 15x and the negative 15x will cancel each other out, and the 3 plus the 10 will leave me with 13. And then down in the denominator, I got 3x minus 2. All of a sudden, things are looking a lot prettier. It looks like this is going to work out. And it's even prettier than you might imagine because dividing fractions is not that bad. The way you divide two different fractions is you multiply by the reciprocal of the denominator. What I'm saying is we can change this division sign into multiplication if we flip this thing upside down. So instead of 13x over 3x minus 2 divided by 13 over 3x minus 2, we get 13x over 3x minus 2 times 3x minus 2 divided by 13. The reciprocal of the denominator is what appears here. And the nice thing about this is now the 3x minus 2's can cancel each other out. So I'm left with just 13x over 13. It's worth pointing out the reason those cancel is because really what this is saying is to take 13x and multiply it by this entire thing. So I can cancel over multiplication. This whole term and this whole term go away. And now the 13's go away, and I'm left with just x, which is what I was expecting to get because I composed together a function and its inverse. Pretty intense algebra, but I think the skills that you get by watching this will be beneficial in this class, namely being able to change some huge expression like this and simplify it. And what that will come down to is getting common denominators and then switching division into multiplication by multiplying by the reciprocal of the denominator. I could do this again, except instead of f of f inverse of x, I could start out with f inverse of f of x. And what you'd see is you'd go through all these steps and it would look a little bit different, but when all the dust settles, you'd be left with just an x here. And the reason you'd be left with just an x is because anytime you compose together a function and its inverse, regardless of which order you compose them in, you're left with just the identity function. The answer will end up just being equal to x. The last thing I want to do is look at the graphs of f of x and of f inverse of x and look for the symmetry that we're expecting from the previous video. I'm not going to ask you to graph these on your own, although you may have learned how to graph rational functions at the end of Math 111. It's beyond anything that I'd expect you to remember for this class. I think it is fair to ask you to graph linear functions like we did in the previous video, but rational functions like this, don't worry about it. You won't have to be able to graph these. But I do want to show you what they look like, so I'm going to pull up some graphing software. Desmos is a pretty good free graphing program that's available online. I'll use it a fair amount in this class. I typed in 2x plus 1 over 3x minus 5, which was my original function, and then 1 plus 5x over 3x minus 2, which was my inverse function. What's pictured is just the graph of the function itself. The graph of the inverse function would look like this. And it's kind of hard to even look at if you just see it in this view. But if I add the graph of y equals x, maybe then you can see the symmetry. If you took this graph in red and reflected it over that line in green, you'd end up with this graph in blue. I know it's hard to see with so much going on in these graphs, but you can kind of verify this if you look for integer coordinate points. Like on the red graph here, it looks like 2, 5 is on the graph. That means that 5, 2 should be on the blue graph. Let's see, 5, 2 would be right here, and sure enough, it is on the blue graph. Well, it's a little bit harder to see in this case than it was in the linear case. We still have the same symmetry between the red and the blue graphs, namely that the graph of the inverse function is just the reflection over this line y equals x of the graph of the function itself. And I think that's all that I want to get across in this video, so I'm going to end this here.